Welcome back, people. Here is the second lecture on audio signal processing, and I will be discussing filtering and reverb, and honestly just a little bit of reverb and most of all filtering, and I will tell you why when we get there. Cool, so what is filtering in audio? Typically we talk about frequency specific attenuation, which is attenuation means decreasing gain, and phase change. So typically we focus on what happens to the amplitude of the signal and less so on what happens to the phase. So it's probably worthwhile thing to say a few things about the phase. So what is phase? Well, we kind of discussed it in terms of what it means for an oscillator to have a certain phase value, and because it's an offset in time, that's what we defined as phase. You really need a reference point, right? So you can't say, well, it has such and such phase. You can say it has a certain phase in relation to something. So obviously in this case it is in relation to the original unfiltered signal. You have a slightly different phase. Now the funny thing or the important thing to understand about the phase is that it's actually a time delay. So the question is, why do we talk of phase? Why do we have a separate term? And the answer is, well, it is a frequency dependent time delay. Okay, so this is quite crucial. So if you have a period duration of 1 second, for example, obviously not necessarily audible as a sine wave, but nevertheless a valid frequency. So if you have a 1 second period duration, then a time delay of 1 second is 360 degrees phase change, or 2 pi radians phase change. Okay, so the delay is 1 second. That the delay that corresponds to 360 or to 2 pi. Now, if I have a tenth of a second period duration, then a 360 degrees phase change or a 2 pi phase change will be tenth of a second, the full length of the wave. So that's that. I mean, that's quite crucial that you see if I have a, let's say, 90 degrees phase change, I would have to figure out what amount of time delay that corresponds to for each frequency. Because for each frequency, a 19 degrees phase change is a different amount of delay. But it is just a delay. Okay, so that's the crucial thing here, that phase is delay, which relates to the frequency. Okay, so filtering, well, first of all, it is very tightly linked with time behavior, and I would say it's inseparable. I hope some of my more advanced mentors and gurus of signal processing are watching this, and at some point there will be discussion. But typically I tend to say that, you know, for a human being, the time is something we measure by clocks, and frequency is something we hear in terms of the height of the pitch. And for us these are separate things, but actually time and frequency are linked, inherently linked, and you can't really separate them. So for a certain frequency to exist, there needs to be a certain duration of time. Okay, because obviously frequency is defined by saying something about repetition in time. So if there is not sufficient time for this repetition to occur, then this frequency may not exist in that duration of time. Okay. So similarly, filtering, so the kind of the attenuation of different frequencies of different periods in terms of repetition is also linked to time. So typically there's two things we're looking at. First of all, that different situations or different, how should I put it, media or obstacles, whatever you want to call those will obstruct the propagation differently for different frequencies. Okay, so different period durations will have a different obstacle in front, and therefore certain period durations may be attenuated, other ones not. Other ones may be accelerated, although I shouldn't say accelerated, that kind of implies the increase of frequency, but the amplitude would be increasing. So typically we have, I'll talk about this in a bit more detail later. So that's one thing. So the medium itself is kind of frequency specific in the way it allows these vibrations to come through. And then typically the way we deal with creating filtering and a lot of filtering around us is actually a recombination of vibrations with time delay. So it's not just the medium, it is the fact that the vibration comes back at itself with some time delay. So typically think about reflections, but I'll talk about this in a second. So why is this happening? Well, it's just because the audible frequencies cover a fairly large range. So if you think about bass frequencies, a few meters, 10, even 20 meters long, whatever it is, 50 millisecond period durations, and then you go to really high frequencies, which have a really short period. So these are relatively large differences, and therefore in physical world periods of these different frequencies, or I should say vibrations at these different frequencies will behave differently. Okay, so let's look at the kinds of filtering around us. So I kind of mentioned the filtering due to transmission. So when a wave propagates in a medium, different frequencies may be affected differently. Typically in air, high frequency roll off. So the more distance you are, the receiver from the sender, the less high frequencies come through. And then obviously vibrations can be transmitted through solids as well. You might know that the speed of sound in solid materials is larger. I don't know if I can say a lot about the spectral response in terms of how it filters, but that's the kind of transmission-based filtering all around us. Now, there is a filtering due to enclosure. So look up Helmholtz cavities. They're kind of a basic chapter of acoustics. You can calculate the resonance of a cavity based on the volume and the neck and a few other parameters potentially. Can't really remember all of those now. In any case, it's a kind of a known thing. If I do this, you don't see what I'm doing, but I'm creating a cavity with my palms and I'm exciting it with the flow of air and I get a pitch. So in doing that, what I'm actually doing when I blow air, I'm blowing essentially wideband energy, and then the filtering has everything to do with focusing, so to speak, that energy to a certain frequency range. So actually this Helmholtz cavity is a kind of a resonator as well, which I'll talk about in a second. Now another thing in terms of enclosure-based filtering is vocal utterances. So the reason why I can articulate speech is because I have tons of muscles that will change the cavities, the shape of my mouth, which is very flexibly changed by moving my tongue. Obviously the opening closing of the mouth. If you probably realize what's happening now, I'm just keeping my nose closed, so I'm blocking away a certain cavity, which again kind of filters the sound that's happening. And actually in terms of the vocal utterance, the vocal folds produce just the buzz, just the pitch, and it has a lot of high frequencies, and then with my with the shaping of the mouth, I'm actually constantly filtering that in different ways. And then obviously I have the plosives, I obstruct it, I have a sudden release of air coming through, and so on and so forth. Okay, so enclosure. Next one, reflections. So this is where we start touching on reverb, because reverberation in rooms is all about reflections. So the question is whether a reverb is a filter or not. Tough one. I would say yes. There might be people who say no, but typically most of the things that reverbs do can be done by filters. The big difference is that the delay times might be much larger for reverb than filtering, but in essence it's a very similar process. Technically it would be difficult to argue that it's a separate class of processes, and especially because when you have a certain kind of reverberation environment, a very small room for example, you get a filtering artifact. Okay, so the two are very closely related, I would say. So what happens when we have reflections? Well, first thing that happens is comp filtering. So I will talk about this. In essence, when a reflected sound is interfering with the original one, what you get is that the reflective path is longer. Therefore, it takes more time for the sound to go through the reflection before it can recombine. And therefore, it amounts to adding the delayed version of the sound to itself. And if this delay time is sufficiently small, then you don't hear an echo, you don't hear a repetition, which it actually is, but you hear a comp filtering artifact, which I will explain in more detail a bit later. Now, this is actually interference with the reflected sound, so that's the same thing. And then also worth noting is that impedance boundaries reflect sound as well. Typically water surface reflects sound, so you wouldn't say that the water does not transmit sound, just like a hard material does transmit sound, but when the vibration tries to go from one medium to the other, that's what we call an impedance boundary, and this is where a lot of reflections occur. So for example, in our ears, when the acoustic energy needs to become electrical energy, it actually goes through quite a few boundaries and transductions. So first it becomes a mechanical motion through the membrane and the ossicles, and then the ossicles actually excite the fluid. So the reason why it goes to through a mechanical motion into fluid is because if you just expose the fluid to air, it would be an impedance boundary and it would reflect most of the energy. So there are ways of overcoming this reflection issue there. And then obviously there's quite a lot of filtering. I mean, if you model the ear, it's all about filtering the outer ear, the middle ear, the inner ear, which is a bank of filters modeled as it's all about filtering. Okay, next one up, refraction. So refraction has to do with sound waves bending around corners, to put it simply. And one good example is loudspeaker box edges. I don't know if you experimented on or if you're aware. Typically, if you displace your tweeter in relation to the edge of the loudspeaker box, you get a slightly different sound. It actually contributes to the response of the tweeter. If you have lovely loudspeakers, likely they have rounded corners. And if you listen to a lot of different loudspeakers, at least that was the case for me, I could actually tell which one had a square box and which one had rounded corners, just because there's something about the box sound, so to speak, something that we can detect, it seems. Okay, so that was refraction. Now diffraction is another acoustical phenomenon that has to do with essentially messing up the reflection. It's a kind of a messy reflection, and one good example is diffusers, things that you might see in the studios, kind of irregular surfaces. Typically we use them to mess the phase up, so to have different phase response for different frequencies, and typically we try to make them quite flat in terms of amplitude response. But nevertheless, if you mess the phase up and the magnitude is flat, it's still a filter. We'll talk about those kind of filters in a bit as well. Now, next one up, so you see I'm discussing some acoustical terms here, is absorption. Good example is walls. So if someone is talking in the room next door, typically I hear the bass frequencies, I don't hear the high frequencies, so a wall will absorb high frequencies more than low frequencies, therefore it acts as a filter. And then last one here is due to resonance. So typically what you have is that certain objects can focus the acoustic energy to a very narrow peak. Okay, so there's a lot of examples. I came up with kazoo. I don't know if you're aware, look it up. It's the little mouth instrument that kind of amplifies the pitched content of your sound. It's actually a little membrane inside. Reeds, you could also call resonant things, which are highly nonlinear, by the way. So we'll talk a bit about nonlinearity, but much more in a forthcoming lecture on distortion. But what that means is that you will get a different response based on the incoming amplitude. Okay, so typically when we discuss filtering in an ideal situation, the response of the filter is not input dependent in terms of the input's amplitude. So if you play it loud or play it soft, it has the same response, but nothing's really ideal, and actually musically you might find that nonlinear things are more lively, more rich. So we'll talk about nonlinearities in much more detail later. Okay, so those were acoustical filtering scenarios. We can talk about electroacoustical filtering. I was trying to cover ground here. But it does happen. So electroacoustical transducers are typically the things we deal with quite a bit, which are microphones and speakers. And the way the electroacoustic transmission happens is typical through mechanical motion. So we make systems that either are excited by air or that move the air. And then from that motion, we get some electrical signals. So what happens in there, typically the bits that cause a lot of filtering is friction for the mechanical movement and inertia. So the fact that the mass of the body as it starts moving, it actually takes energy to stop it. So it kind of goes on of its own once it's in motion. Just to cover wide ground, these things might be interesting as a broader understanding of filtering. And then finally, electrical filtering. So here we can talk about the current transmission. Obviously we do this in metals. Copper is typically the metal that we use. It has quite a flat frequency response for audible frequencies. It does break down for extremely high frequencies of processors, and things start happening there. Electrolytes are fun. So liquids with some kind of ions in there, or acids, salts, all of these things will conduct electricity, but in a less ideal way compared to metals. And actually it's kind of happening now. There is a company, Agnew Electronics. They make kind of how do they call it? Electrochemical synthesizer cell. I've done stuff with aloe vera leaves because they have a certain spectral peak and distort in a funny way. And then recently I saw a guitar pedal which you can fill up with any liquid you prefer, and it kind of produces a distortion effect based on transmitting sound through liquid. And then interestingly also springs, right? So that's kind of an electromagnetic, I should say, system. But it has a certain filtering effect, and there's a lot of reflections, and you see actually it produces a reverberation kind of effect, a spring magnetic excitation of a spring. So there you see again how actually these things are closely related. Okay, so that's the transmission. Then we have capacitance. So typically capacitors do this. If you put them in series of an electrical signal, you get a high pass filter. So it passes high frequencies because the load can jump over the electric plates. But if it's a slow rise and decrease of voltage, then it won't pass through. So it's a high pass filter. If you link it to the ground rather than put it in series, then you get a low pass filter, because then you're essentially sinking to the ground all the high frequencies and the low frequencies can pass. And the other way around is the way that coils behave, which are inductors. So due to inductance, you would get a high pass filter if you put it in series, and if you ground it, you get a, that's the other way around. I should correct that. So low pass filter in series and a high pass filter if you ground it. And then comes the digital filtering. So the content of this lecture really is all about digital filtering, as you might expect, which is a very complex engineering topic. I mean, if you ask me to design a filter or to go through any of these equations, I'd probably skip that. It really is good engineering subject, and obviously you can get some insight into how it works, but it's actually really serious science behind designing digital filters. Quite exciting. Okay, so that's the kind of overview. I'll explain a few terms here just to be clear. So damping in terms of audio modification relates to reducing the length of resonance. Okay, you will hear people use the word damping in a loose manner to cover in a kind of a metaphorical sense. So it could be a lot of things, but typically if you're in a more how should I put it, academic environment, then damping should strictly mean reducing the length of resonance rather than filtering. Some examples there for you: towel bass drum heads, piano dampers, and so on and so forth. Now, next one up, muting. So this one should change the frequency balance as well. We have mutes for violin bridges, for brass instruments. You might be aware of these things, which are also kind of filtering the sound. And in terms of how things are filtered, well, you can look it up actually. There is some interesting materials on how we describe different frequency ranges. Kind of recording engineers, mixing engineers like to have a clear picture of what it means when something is dark, thin, hollow, nasal, in terms of how the spectral shape is. I won't go into that. And then here comes the resonance again, so blowing beer bottles, striking tuning forks. So you actually convert the broadband energy into fewer or maybe only one spectral peak. Actually, I wanted to put in vowels. Normally when I lecture, I have a lot more jokes to come up with because the presence of an audience is inspiring, or the other way around, the presence of people who are not very excited makes me want to excite them, so I say a lot of silly things. And with these online lectures, I have to say they're a bit dry, but hell. So I wanted to put vowels in here. So vowels, you know, your the last stage of your digestion tract. Because there is supposedly, honestly I didn't check it, although I do check quite a few things, but this one I didn't quite. There is the so-called brown frequency, which makes you go to the toilet and poo. excrete. And there is quite a lot of, I may be informal bullshit about different parts of your body resonating to different frequencies, healing frequencies, all those things. Maybe it's a good moment to say something about these things. It is quite obvious if you study acoustics that for an object to have a narrow band resonance, which means that it responds to a certain frequency only, so to speak, it has to be rigid. So typically, well, I have I'm not sure if I have a cymbal hanging here, which is a rigid object, and it has quite a few resonant frequencies. It has a very complex spectrum. But if an object is limp, if it's packed with water, if it's actually body tissue, it does not have a narrow band resonance. It has a broad band resonance. So what does this mean for the frequency that makes me pull? It means that it's not actually specific frequency that does that. It is more the frequency range and the energy of this oscillation of this sound. So I think they say it's about 6-7 hertz. I don't even know what they claim, but I'm pretty sure that if I go to pull from a really loud 7 hertz sound, it will happen at 5.5 hertz as well. Okay, so typically the audible frequencies, you understand that the size of the object matters and the rigidness of the object matters a lot. I don't want to say anything about, you know, resonance of molecules in cells or cell membranes. These are very microscopic things. Suffice it to say that they would need much higher frequencies for them to be responding, and they need some rigidity in order to have a narrow band resonance. So things like 432 hertz is good and 440 is damaging. It's just a load of bullshit. Thank you for following through this little rant. Okay, so here we go with basic filters. So typically everyone understands, everyone who approaches digital audio signal theory, that we're talking about frequency domain effects. I kind of try to expand this to time domain effects as well, because they do affect the properties in time. The important thing is that filters do not create new spectral partials. So they amplify or attenuate existing ones. They do not create new ones. Non-linearities, they create new partials. Distortion type effect. So we will go into this probably in 2 lectures time. So the ringing, which filters do, is actually resonance with long time decay. So it's not a new frequency component. I mean, if you didn't hear that specific frequency in the original sound, it wasn't accentuated. You might think, oh, well, that's something new in the sound. It suddenly rings. Well, actually, it doesn't really, because that's just an exaggeration of what was in there already. Obviously, you have something that we call self-oscillation in filters, but that has to do with the feedback loop with high gain, such that the energy is getting recycled and keeps recycling, or actually increases, which is a different case. Another worthwhile term to coin is the spectral envelope. So it is the shape of the spectral property of the peaks in the spectrum. So that's what changes. And it's worth noting that in terms of our understanding of the sounds around us, we do hear the spectral envelope very clearly, but not very consciously. We tend to hear it as the body of something, because typically in the acoustic environment, the body sizes don't change very easily. whereas the excitation mechanisms do. So typically, if I take a guitar, for example, the excitation mechanism is the vibrating string, and the body of the guitar is the filter. So what you get then is that you recognize that it is the same guitar. You recognize different tones on the same guitar because different set of excitation signals are filtered in the same way. And that's why in basic sound synthesis, it's sufficient to put a single low-pass filter on an oscillator and you already get a sense of a character of there being a body to a kind of a fixed thing. And it's actually difficult to hear it out. So you really need to work on your analytic listening to kind of figure out, okay, what is the character, because it kind of fuses, it makes a higher level understanding of the object rather than allowing you to listen into the detail of the spectral envelope. And by the way, if you do more advanced pitch shifting, then typically you would reapply the spectral envelope, because then you would get a sense that the source is the same object, but the pitch, the excitation signal is changing. Otherwise, if you, for example, pitch shift a speaking voice, you get the chipmunk effect. So the size of the head seems to be smaller. You get a kind of a miniature person rather than the same size person speaking on a higher pitch. Okay. And then probably not gonna do a lot of this, maybe a bit in the exercises, but actually we can use filters in different frequency ranges, obviously. And if you have sensor data, so much slower data, you can actually smooth it out. You can extract the sudden motion out of this. So actually filters can be used in that sense as well. Let me think. I didn't plan doing much on this, so it's probably worth completing this little thing by saying that if you low pass filter a motion data stream, then you will smooth it, so the ripples will get smoother. If you high pass filter a data stream, and we'll get to this, then you will lose the slow motions and retain the fast motions. So you see how it relates to high frequency being fast motion, low frequency being slow motion. And if you band pass filter it, I mean, it's kind of funny because I'm about to define these things, but if you band pass filter it, then you actually get a certain speed of motion to be accentuated and the others get attenuated. Cool. So a good term, you will hear me use this one fairly frequently, is the frequency response. So it's one way of describing a filter. So typically what we are talking about is gain of the filter across the frequency range. Typically you might have a gain expressed in a kind of a factor, multiplication factor, or you can have it in dBs. I won't go into the details on this or problems with this, keeping it practical. This is the spectral response of a gain stage. Okay, so what this tells you is that the gain stage has a flat spectral response. So a multiplier is a gain stage, which means that if you multiply a signal, then all the frequencies will be of equal level after the attenuation. And in this case, it also tells you that if you halve the amplitude, if you multiply by 0.5, that's a -6 dB change in gain. I will talk about dB scale. I think next lecture I will talk more about the mathematical, arithmetical backbone of audio signal processing. Okay, so let's discuss the basic filter types. I think I'll run through this mostly. I kind of expect most people who engage with this to have a good sense of these terms. So low pass filter, as it says, it passes the low frequencies and it attenuates the high frequencies. The parameter, the crucial parameter, is the cutoff frequency. So at a certain frequency, we say that this filter starts to take effect. Now, the way the filter starts to take effect is really gradual, normally. So it's really difficult to pinpoint that exact moment. So that's why engineers came up with the -3 dB point. So as soon as the response has dropped 3 dB, that's the point that we call the cutoff frequency. So in practice, if you have a cutoff frequency of 400 Hertz, you may understand that there is already something happening at 380. Okay, the other set of terms which are useful is passband, which has to do with the band of frequencies which are unaffected. We have the transition band, typically, and the stop band. Now this is somewhat ideal, this response. Luckily it's not scaled here to -infinity, otherwise it would be totally ideal. But it's a good general sketch, and then we also define the bandwidth, which is the width of the passband. High pass filter is the other way around. So passes high frequencies and attenuates low frequencies. The terms are the same. -3 dB point is the same. Band pass filter is a kind of a combination of the two. So you have two cutoff frequencies, and using the two we define the one center frequency. So typically, if you're accurate about these things, a band pass filter has a center frequency rather than the cutoff frequency. And then it has two stop bands, one pass band, two transition bands. This is how you define the bandwidth there. Now, in terms of band pass filters, what we have is another way of defining the bandwidth, which is Q. And Q is a way of defining the bandwidth that relates to frequency. And in doing that, it is actually perceptually more relevant. Okay, because if I have a band pass filter and I have 100 Hertz bandwidth and my center frequency is 150 Hertz, then I get two corners at 100 and 200, and that's 1 octave. But the same bandwidth of 100 Hertz at 1000 at 1K will be about semitone or a major second. Okay, so perceptually, as the frequency increases, the same bandwidth in Hertz is actually progressively smaller, and that's the issue. So if you use the Q factor, then you compensate for that, and thereby you get a sense of bandwidth which is more close to how you hear it, which is a kind of a logarithmic exponential thing. So here is the equation, center frequency over bandwidth. So you see the higher the center frequency, the more Q. Okay, I think that's a fairly sufficient description there. And then band reject filter, or otherwise a notch filter, kind of the opposite of the band pass. Similar set of parameters, except the stop band is in the middle, two pass bands on the sides. Worth noting, although it's kind of evident, I would think, that if you combine filters, make sure you understand what happens, because a series combination, one after the other, will produce a different result from a parallel combination. And if it's more complex filters, if we look at the delay, the phase response of the filters, then the thinking process gets slightly more complex. We'll talk about this in a second. Okay, so here comes the interesting bit, which is how on earth does this happen? Okay, so I mean, to me, I almost still remember when I started loving signal processing. And I realized that, you know, what is a signal? Okay, fixed frequency, sine wave, kind of figure that out. Figure out the noise, okay, broadband, Why? Not quite sure. Well, it does the thing. It sounds really dense. And then things in between. And then, for example, I look at the plot of a low frequency and a high frequency added together. Actually, maybe it's a good time to do this as well. So let's look at that. Let's have a sine oscillator at high frequency, let's say 10K, and let's say what should I do? Some unrelated number, so they don't go in phase. And then what I do is I put the frequencies in an array. I talked about this, so they automatically expand. So I get 2 sine oscillators, and then I can sum them to get a single sine oscillator, and then I want to plot this. I think this was late for the... Here it is. So this is a sum of a low and a high frequency. Now, what the filter would do is it would separate these. Okay, so that would be 1, and then, well, let's do this. So let's plot those 2 as well. Okay, so this waveform is being separated into these 2 waveforms in an ideal situation. And if you kind of try to get there from basic understanding of math and values and arithmetic, multiplying, subtracting, it is really puzzling. I mean, I found it tremendously puzzling. It's like, how on earth do you take this set of values? So obviously it's a digital signal, so there's a lot of values one after the other, a series of numbers between -1 and +1, actually -2 and +2. And what on earth do I do? What kind of combination of multiplication, subtraction, powers, differential, what on earth can I do in order to get these 2 out of that? So it really is a mind-boggling situation. And to be honest, it took quite a bit of digging before I understood why and how this can happen. So part of the reason I'm trying to stress this question is because you know, that's the way people learn. I mean, if you're not interested, you might learn, but you will forget really soon. So typically, rather than giving answers as a lecture, I think it's more important to really produce questions that are burning, that make you really excited. And actually, I would struggle to kind of throw out the answer here. It's like, okay, well, that's how you do it. Because it is still quite, I mean, it's horribly simple, but still complex in a way. So let's look at this. So what actually happens in a filter is really simple. And hopefully by explaining that, we'll get to the separation of those signals. But actually, the simplest low-pass filter is just about adding the previous sample to the current one. And that does a low-pass filter. So that's another hopefully mind-boggling situation. How on earth does that create a low-pass filter? So let's look at that, and I will create that in code, adding the previous value to the current value. But I won't create it on the server. I can't really in SuperCollider. I'd have to code C++. So I'm just going to work with lists, and we've discussed lists last time, so that should be helpful as well. So what shall I do? Well, let me just take a random array, okay? So I will make an array of values, random values, and then size. whatever 24, minimum -1, maximum +1. Make it look like an audio signal. I will call this A, and what did I do? Oh, +1. Oh my god. Okay, and then obviously I want these to be floating point values as well. There we go. And then I can plot that. So this is my signal. So the question here is, what on earth happens if I keep adding the next value to the previous value? So you kind of see here the corners are actually sample values. That's the way this plot works. It kind of connects the dots. But actually these are just values, so you can probably even trace this. So first one is -0.1, which is this, and then -0.6, +0.9. So these are the actual sample values. And then I can create a function that does what I've just asked it to do, which would be take an input value and yield an input plus the previous value. Okay, so that looks nice and simple, but it has to be slightly more complex, because what I need to do also is I need to store the previous value. Although I could do this more simply, because I have the array of values just there. And this is maybe a worthwhile moment to say something about signal processing. Typically everything that I will show you, and most of the things that run on computers in terms of audio, are real-time processes. So you don't really have all the samples available, because it could be a live signal as well. So that's probably one of the things that I should have said about this separation, is that, you know, if you ask me to do this from this data set, I would be like, okay, well, probably come up with one way or other of describing a process and then maybe formalizing it. But if you tell me that I have no clue what's going on, I just get every next sample as I sit here, and the next one and the next one, and from that to separate them, which means in real time as they come, it's even more puzzling. That's the challenge here, because I need to do this in real time as the samples come in. Okay, so how do I do this? Well, what I can do is I can create a function enclosure on top of this one, which will be my filter. Bloody hell. So my filter is this function, and it will return a function that I can run. Okay, and the reason I do this because it allows me to specify variables that will survive this scope. Okay, so here I can specify the output. Well, actually all I need to do is specify the previous value, because you see when I run this function once, it just runs, and the next time I run it, it just reruns the whole thing, so it has no way of storing away a value. I mean, I could store away a value in a global variable, but it's probably worth showing you a generator. This is part of functional programming strategies, and it's really neat in SuperCollider. Part of the reason I love it. So what I'm doing here then is I'm saying, well, previous value will be the in plus previous value, and we'll start off the previous value with 0. Okay, am I doing this right? So if I say this is my, actually I'll call this the generator, G, that's the term from Lisp. And then what I will do is I will say that F, which is my filter, will be a G dot value, or just empty brackets. Okay, and now I have a filter, and now I can run numbers through it. Okay, so I can verify that it's doing this thing. So if I send to a filter number 1, it outputs 1. Why is that? Well, because the previous value was 0 and the incoming value was 1. Now if I run it again with number 1, I get number 2 because now the previous value was stored away and it was 1, so the next one is 1. So actually I can keep increasing this value. Now if I run it with -2, I'm back to 1 because the previous value was 3 minus 1. -2, sorry, equals 1. Okay, so that's this procedure, add the previous value to the current value. Okay, so now let's run that. Let's run our random array through that. How do we do this? Well, actually there is a shorthand, I believe, but I'm a kind of an old school super collider guy, so I don't really use those fancy new things. I mean, fancy new, probably about 10 years old now. So what I do is I a.collect, which means I'm gonna run a function f for all the elements of the array A and store all the outputs in a list. Okay, now I will reinstantiate a filter, which actually gives me another filter where the previous value is 0 again. And I will say that the b equals a.collectf. Okay, so let's plot a against b and see what happens there. Okay, so the a is my initial function and the b is my added previous value to the current value function. So what you see is that actually I'm smoothing the waveform out. So you see there's many more peaks here. The peaks, I should say, are sharper, and here they're actually softer. Okay, I can try to run this on a larger data set as well. Let's do 124 new filter those things, and it's even more evident here that actually I have taken the slow motion out of, so I've attenuated the really sharp things in there in this waveform, you see, and it actually highlights how the average goes on. So you see, from this waveform I wouldn't really be able to tell visually that most of these values are positive. I mean, if I look at it, then I see that the positive peaks are kind of wider than the negative ones, which are narrower. But if I look at the low pass filtered version, I actually see that quite nicely, and you see how this wider positive peak becomes something like that. Okay, so that's what happens if you add the previous value to the current one, because it is a kind of an averaging thing, right? So if I actually wanted to make this an averaging filter, then what I would need to do is just yield the half of that output value. Okay, so I've stored it away, which has not been scaled. So it's actually always adding the two values, but what I'm outputting is the half of that without without changing what the previous value is. I hope that is clear. And then, surprise or not, what happens is that I get the exact same waveform, because what I've done with dividing by 2 is I've just halved the amplitude. Right? So that's the message here, that the basic averaging of values is a low pass filter, because it smooths out the waveform. Slow motions are low frequencies, fast motions are high frequencies, so a slower motion is necessarily richer in low frequencies. And actually that's type of a filter. I actually don't have it in the slides, but averaging filter is a term, and typically I could average across multiple values, not just 2, but I won't go into that now. Okay, so that's this thing, adding the previous value to the current value. So this is a difference equation which explains exactly that. And in these equations, y is the output, x is the input, and these indices, they highlight the order of the samples. So n is a current, xn is a current input sample, yn is a current output sample, and xn minus 1 is the previous input sample. So this thing says the current input sample is the current output sample is the current input sample plus the previous input sample. And this is the sketch. So this is kind of a straight through line, and I'm adding the delayed sample here. Z to the power of minus 1 is a single sample delay. You'll see this very frequently in filter sketches. So it just delays the samples by 1, and that's my output, and that's that. Cool. So hopefully that was exciting and cathartic. And then I'll go into, this is the kind of thing you won't really see in textbooks, because people typically start with the FIR. But I kind of find this really interesting to grasp, because that's the basic mechanism. It's just the previous and the next or the current sample. Now, with an actual first order finite impulse response filter, which is something that you will see in textbooks, the difference is that I'm scaling the current input sample and the previous sample with an inverse value. So I have one filter coefficient, which is A, and then the current sample is scaled by A and the previous sample is scaled by 1 minus A. And what this does, it kind of preserves the energy across the filter. Obviously that's now would be getting into the filter design. I definitely don't want to go there. But just so you understand how it's actually the same underlying structure with a different scaling. And most of the filter design is actually coming up with these filter coefficients. So obviously as you get more complex filter, they will have more filter coefficients. And typically the way you would like to control a filter is you want to say what is the cutoff frequency, and to translate from cutoff frequency to filter coefficients is not trivial, and I'll leave it at that. Okay, so how about this first order filter? It's worth noting that it's first order because it uses only the previous sample. If you have a second order, it will use 2 previous samples. It actually relates to the first order and higher order filtering in electronics as well. So typically one coil will produce a first order filter, 2 coils a second order filter, a coil and a capacitor is also a second order filter. So in electronics is the amount of these filtering components, and these things behave in rather similar ways. So the slope of this first order filter is 6 dB per octave, and for each next order you increase more dBs. Now it is worth thinking about this figure. So how many octaves do we hear? Well, bloody hell, I think piano has about 7 octaves, a bit less, 6.5, something like that. And these are not, this is not the range of audible frequencies, this is the range of pitches. If you're interested in that, I have a video on psychoacoustics, goes in more detail about what that is. But even then, that's up until, what is it, 2K, 2.5K. So above that we have maybe 3 more octaves. So I think it's safe to say that we hear about 10 octaves. Okay, so the point is, what that means is that I have a first order filter in the lowest octave, then 10 octaves up I will have a 60 dB attenuation, and that is still audible. Okay, so that just says something about the amount of attenuation what you can expect from a first order filter. Okay, now important, the filters will alter the phase of a sound. I'll talk about that in a second in some more detail. which can be audible. Okay, so we had a little play with shifting the phase of fixed frequency oscillators and trying to hear out the difference. And it's tough, but if you have really clean transients in your sound, attacks, especially if they're acoustical or origin, so you kind of recognize the crispness, the truthfulness, the fidelity of the recording, then you put on a stupid filter and you hear, there's something about that attack which has changed, rather than just the kind of the spectral balance. And typically, if you mess up the transients, you get a sense of something sounding more distant. Okay, I think I'm talking about this in psychoacoustics lecture as well. Won't go there now. I'll talk briefly about the infinite impulse response filter in a second. So let's just briefly look at the phase response. So this is what happens with the phase of a low pass filter. So we have this frequency response. This should be fairly clear. This is actually originating from an electronics engineering slideshow somewhere. So the terms are slightly different, but that's why it's also worthwhile. So typically they would talk about slopes in decades and not octaves. So decade is a tenfold, and octave is a twofold. And this is actually equal to 6 dB per octave. The other thing which is interesting that you don't find in digital audio textbooks is that they actually define the 3 dB point in terms of phase shift as well. Okay, so how do we understand this graph? Well, I kind of introduced the concept of phase in a way that makes this really clear. So if I delay a signal by one sample at the maximum frequency, and actually I've added it to the previous one as well. So at the Nyquist frequency, if it was just delayed, it would be the opposite one. So if you remember from last time, at the Nyquist frequency, I have one sample max, the other one min, one peak, one trough, one peak, one trough. That's the maximum encodable frequency. So if I shift that by one sample, I actually get 180 degrees phase difference, right? Because instead of the peak, I will get the trough. Now, if it's a filter like that, when I've added the previous sample to the current sample, then that becomes half of that. It becomes the 90 degrees phase shift, right? So that again has to do with adding up sine waves. If you add a 0 degrees phase sine wave and a 180 degrees sine wave, you get a 90 degrees sine wave. Okay, so actually that's what happens here. At the Nyquist frequency, I get a minus 90 degrees phase shift. Okay, and then at the cutoff frequency, I get a 45 degrees phase shift. So actually I could potentially figure out the cutoff frequency for this, but I'm afraid I'm going to say stupid things because I'm not a filter engineer. If you need one, let me know. I'll call one up and he'll sort us out. And this is the crucial thing. So you will get a phase shift. So all the high frequencies coming out of a first order low pass filter are delayed. Not much, but a little bit. And even more importantly, they are delayed in relation to the low frequencies. So typically for a low frequency, a one sample delay hardly does anything, right? So as you increase the frequencies, you actually increasing the delay or the phase shift, the negative phase shift, and thereby you are messing up the transients, right? So that's what I was saying. So if you have a transient where all the frequencies jump up instantly, that's a transient, then what you get after filtering is that some frequencies are late in that initial impact. Okay? Cool, so that's that phase response. Here comes the infinite impulse response filter. So it's similar to the finite impulse response filter. And what this one has instead is a feedback loop. Okay, so the difference here is that I'm not adding the previous input value, I'm adding the previous output value. You see, so there is a feedback loop, so I'm storing away the previous output value. And actually it seems, let me just check. Yeah, so what I've done here is I've added the previous output value rather than the previous input value. So actually this was an IIR. Honestly, I didn't intend it, but that's how it came out. And the difference is not huge. It will have a similarly 6 dB per octave slope. Obviously for engineers, it's a different way of calculating the coefficients. For audio people, it's worth noting that infinite impulse response filters are less stable. They can blow up and do funny things. That's about it. I won't go into more detail. So, but one thing I want to go into, so now we have this first order filters discussed. And the question here is, how do I make it a high pass filter? Okay, because you might know that a first order filter, an IIR and FIR can be a high pass and a low pass. So the question is, how do I do that? And the answer is really simple. I just have to subtract the previous value. Okay, so why is this? Well, let's look at the plot and then hopefully I can explain that in some detail. So now I'm having a filter that subtracts the previous value from the current value. And here is the plot of the two waveforms. So what happens here? Actually, maybe I should, maybe it's worthwhile if I do all three. Okay, so I'll have an H. So the first one will be a low pass filter. H will be a high pass filter. So F is the low pass filter. E is the high pass filter. Not great. This complexity of code grants or desires better variable names, but I'm being quick and dirty. So B is that, and then C is the high pass filter version, which is a collect E. Okay, and then I want the ABC plot. Great. So this is the original signal. This is the high pass. Sorry, this is the low pass and this is the high pass. So what has happened here? So you see here I've been averaging the values and I get the slow motion. And here I'm subtracting the previous from the current one. So what that does, if you imagine if I have a very slow movement, it will actually exaggerate the peaks. So that's the kind of way of understanding it. And what you have here is exactly that. You see the slow motion inside this waveform is omitted. It's all neatly zero-centered. And all I get is these very high peaks. And that's that really. That's my little high pass and low pass filters, adding previous values and subtracting previous values. So I think I'll leave it at that. I think I'm taking quite a long time with this one, although it is a horribly exciting thing to understand filters, I believe. Cool, so let's go on to slightly more complex filters. So I've mentioned the term comp filter. It happens when the sound is reflected off the wall next to you. It happens when an airplane flies by. If you've ever wondered why does it sound a bit like a flanger when the airplane flows by, it is because it's actually a flanging effect. What happens is that if you're stood here, let's say on the ground, here at the bottom, and the plane flies by, actually what you get here is your ear, because you have a certain height. The effect should be much less if you lie flat on the ground. Hopefully you didn't get to lie flat on the ground when airplanes were passing by, unless it was stupid me, sorry. So a plane is flying. What happens is that you have a direct sound and then you have the reflected sound of the ground. And as the plane approaches you, the delay difference is getting gradually, progressively smaller. Yeah? So you actually have the reflection time being lesser in relation to the direct wavefront, and therefore you get these notches to move, and that's what a flanger effect is. Okay, so a flanger is typically just a sliding comp filter, and this is what happens. So, but let's first discuss why does this produce a set of notches. So what I have here, you see, it's the exact same thing as my initial filter, except it's not one sample delay, but it's a longer delay, a delay of more samples. So I'm just adding the delayed sound to the original one, but the delay is significantly longer. And what this does, it again relies on destructive interference. So what happens is that for certain frequencies, this delay time will mean 180 degrees phase shift, will mean total annihilation at that frequency, because it just comes back with the inverse phase. And for some frequencies, this delay time will be exactly in phase with the period duration, and therefore you get a reinforcement. So you see, actually, if you do this at these frequencies, what you will get is a dB increase, 6 dB, doubling the amplitude, and then minus infinity, supposedly, when it really hits those values. So you can think about it. I mean, let's say this is 10 samples delay. Okay, so what is the period duration for which this will be a reinforcement? Well, obviously, if it's a 10 sample period, right? Because if I delay the waveform, the periodic waveform, by the exact duration of that waveform, then it lines up perfectly. Okay, so it's full reinforcement. Now, what would be the frequency for which this would produce a total annihilation? It would be the frequency which is half that, which is 20 samples long. Because if it's 20 samples long and I delay it by 10 samples, then I get exactly out of phase. Okay? And then the funny thing is, what happens if it is 30 samples long, 40 samples long? Can I think about those? So let's say if it is 20 samples long, then the 10 will be, as I said now, that would be total annihilation. If it was 40 samples long, it would be 90 degrees. Am I saying that right? I think so. So that would be somewhere down here. But there is a cyclic property to this, and it's actually apparent above those simple cases, right? Because actually what I was talking about, if it's a 10 sample period and a 10 sample delay, then that's, what am I saying? 20, I said. If it's 20, that would be this point of total annihilation. And then as you decrease the frequency, then you're kind of getting up there, and the longer it is, essentially, the less phase cancellation you get. And there is no next notch there. But if I go up in frequency, so I had a 10 sample delay, and I said, what happens with the 5 samples? that would again be a peak. And what happens with the 7.5 samples, I believe that one is a trough. I'm not going to go into verifying this, but there is a cyclic nature. Maybe I'll make an exercise about this. Probably should be nice to see these things happening. As I said, never believe a lecturer because you're making him a priest. You believe, you trust the priest. In science, you're skeptical. You assume what someone says and verify it. Okay? So go ahead, do it even without me making an exercise. Verify that. Take a piece of paper, draw these things out for yourself. I mean, it's just invaluable to realize something, to, you know, prove it to yourself rather than assume it. I think it's so important. Cool, so that was an FIR comp filter, so we were delaying the signal, adding it to the original one, and in a feed-forward fashion. And then the infinite impulse response comp filter will do a similar thing, but with a feedback loop. So the difference here is that with the feed-forward comp you have notches, with the feedback comp you get peaks. You can kind of remember this because if it's a feedback it tends to whistle, so it's a sharp peak. Okay, maybe that's an easy way to remember. And then here is also the plot of the phase response of an IIR comp. So you see that there is quite a lot of mess going there, happening there. And what you see is that at the notches, what am I saying here? So the 0 phase is at the notch. Hell, I won't go into this. I'll try to round this off. It's taken a while, this lecture. I hope you're still here. If you're still here, say yeah. Great. I can't wait to have real lectures again. It really is more fun if I see people. Okay, so all-pass filter. So what happens with the all-pass filter is that the magnitude response, the frequency response, is flat. So there is no attenuation in terms of amplitude, but there is things happening to the phase. So we can create filters whereby we shift the delay times at different frequencies, but the magnitude, the spectral response stays flat. And this is one simple version. There's many different all-pass filter topologies. And the funny thing is that it's actually two comp filters on top of each other. So you see here is the feedback comp and here's the feed-forward comp. And it kind of makes sense as well, because if you look at the two magnitude responses, where you have a trough here, you would get a peak there, and actually they add up, and thereby they produce a flat spectral response. And then obviously I don't have the phase of this one, but you can assume it, don't assume it, look it up. The phase will be scrambled. Phase rotator, here is the phase response of an all-pass filter. Gets more complex here. I won't go into this. I'll try to round it off. So briefly about reverberation. Typically, we use comp filters and all-pass filters and delays. This is the simplest, earliest design, Schroeder's reverberator. We have comp filters in parallel and all-pass filters in series. The reason is that comp filters have these peaks, as you've seen, and you want to add these peaks up. If you put these peaks in series, then they will cancel each other out, so you will get less peaks. So what you want from a reverberation is a good dense amount of peaks. And the all-pass filters, they shift different frequencies, they shift the time for different frequencies, the phase of different frequencies. And if you put these in parallel, then you would get cancellations, right? Because different phase shifts. We've looked at this. So you really want your all-pass filters in series. Okay? And you can experiment with this. It really is tough to make this sound decent at all. So, another big chapter. I hope you're still with me. I guess so. Let me stretch a bit. Deep breath. A little break. I don't have a beverage here, which is a mistake. But I'm all up for it. Let's do this. Impulse response. So what an impulse response is the signal that comes out of the filter after sending it an impulse. Okay, so actually I can create that right here. What I can do is I can do an array fill of whatever, let's do 50 values, and all of these values will be 0. Okay, and I can do an array of number 1 plus plus that. So this is my impulse, and then I can take this impulse through my low pass filter and my high pass filter, and then apply that filter to the A signal and then plot that. Okay, so that's what it seems to be, I guess. So the thing is that this is not a truly good one because I don't have the coefficients. Shall I add in the coefficients? Well, now that we're here. So what was it? I multiply the... I have an A coefficient. I'll take 0.9. And then what I do is I multiply the input signal with A and the previous value with 1 minus A. Okay, so let's hope I've done that well. Otherwise we'll be here all day, all night. Let's do that. And let's not do the averaging. I should have taken out the averaging for the high pass anyway, but it's obviously just a gain change at the end, so the shape of the waveform is not affected. Let's hope this does a better job. Ooh, no. Message X. Hey, what did I do? Okay, I was in a rush. Functions look good, function looks good, and then here something went wrong. Collect, not understood, 0.9. Oh, because I'm reusing the A. Horrible, horrible. This will be my cough, which is the coefficient. Okay, you see, I said it, I felt it. I said it, I shouldn't be using these horribly abbreviated variable names. I'm trying to save time, save life. Never useful. Always enjoy the journey. Forget about the goals. Take a deep breath. Love life and hate material possession and achievement. And when I was saying that, obviously I was still rushing ahead. Okay, shall I actually go through these things? Let's see, I close all of this. So is A still the A? No. So how did that happen? A is A. Okay, and then there is no further A's in here, I hope. Okay, cough. Oh, sorry. Oh, stupid me. That's that. That's why it broke previously as well, because that A would have been inside this scope and I shouldn't have changed it either. But that's life. You make silly mistakes as you go, especially if you try to rush. Okay, so that's one of those, and that's the other one of those. And this is what we get, ABC plot. C is A, this is not making sense. A collect E. Okay, this will be an exercise. I won't waste more time. But in any case, you saw me create an impulse response, and then it will be cool to see the impulse response of low pass, high pass filters, comb filters. It will all be the exercise. I'm really wrapping it up now. I hope you appreciate. So impulse response is a term that you might have heard before in the context of reverberation. And the reason is that we can describe the effect that a space or a set of reflections has on a single sound. So this is a receiver, this is the emitter, the sound source, and then you have the direct sound, but other than the direct sound, you also have reflections. Now each reflection will take slightly longer to arrive to the receiver, so that's why we use an impulse at the sender, because then we get a clear picture of all the reflections. Okay, so that's the impulse response, and that's how we can characterize filters. So if you think about, so kind of anticipating the exercise, for adding the previous value to the current one, what you will have is just two peaks here, because the current value is coming in, and then the same amount, the same level, the same sample value comes one sample later. Okay, so we'll look at that, and I won't go into that any further. In terms of reverberation, you might know this. Typically we separate the reverberated sound into direct sound, early reflections, late reflections, or the tail. The thing to note about reverberation is that the density of reflections gradually increases. So if you do a very simple multi-tap delay, which is actually very similar to comb filters, right? Because it is just a delay adding to the original signal. So there is an equality between multi-tap delays and a series of comb filters, or I should say a bunch of comb filters in parallel. It's the exact same thing actually. But those things won't give you a gradual increase of reflections, of density of reflections, which is what happens in space. So it's a good way of designing your reverb. Here's a more complex one, where you actually have a separate thing for early reflections, a separate thing for late reflections. This is still a feed forward thing, and typically with reverbs you try to do some feedback thing. Another thing you try to do is modulate the delay times slightly. I won't go into reverb in any more detail. It's a really interesting, exciting engineering thing, and it's really not for instant gratification addicts. It takes quite a long time before you get something worthwhile, unless you do impulse responses and play with that. That's a bit quicker to do. Okay, so we're at the end here. A few more complex filtering mentions. If you see something called a resonant filter, it is designed to ring. Dynamic filtering, so typically changing parameters over time, can be cool, wah-wah, sweeping effects, auto filter, other things. Nonlinear filtering is an interesting chapter just because we are modeling analog gear more and more, and typically in electronics nothing is truly linear, so all of these EQs filters are non-linear. They distort as well, but the amount of distortion actually makes the sound, you could say, better. I mean, you know, the exciter, I will talk about this in distortion, is actually distorting things, reducing the fidelity of the signal, but we perceive it as the increased fidelity. Matching filters, that's an error there. So typically you can analyze the spectral envelope and recreate it. What is the term? I'm thinking of a term, I didn't put it here. Linear predictive coding, LPC, is kind of an old school way of analyzing the spectral envelope, and then you can recreate a filter from it. And as it's called linear predictive coding, it kind of goes into predicting the future values of a signal, so you can do that as well. So which is a funny thing because it's the same thing. So if you create a matching filter, I won't go as far as to claim it, but I can suggest that you can predict, you know, processes in nature, because you're kind of extrapolating what's going on. You assume that the spectral character of the signal stays the same, and then you can extrapolate that. And then something similar, which is quite popular now, when you flatten the response of your speakers in the room, and where you do a similar thing. You analyze a spectral envelope, but then you inverse it, smooth it as well, and then you get a filter that will make your room and speakers sound flatter in combination. Cool, so that's that. I will paste these links into the comments of the video. This last one is just great. I mean, if you really want to dig into filters, EQs, digital, analog, all of these things, can definitely recommend this, but also the others. Thanks for watching. Bye.